Okay, Jit. Fine. Rick and Keval, good morning. So we continue with the recursive definition of the reverse function. Version 1 we had discussed yesterday. Now a small modification is there in version 2, the right column, splitted right column, the second column, where rule number 2 changes to reverse AX equal to reverse XA. Compare this rule number 2 with version 1, the left side column, where reverse XA is A reverse X. So if you look at version 1, point number 2, rule number 2, then what we are doing, we are making the last symbol the first symbol in the reverse string. Reverse of XA. A is our last symbol. A belongs to sigma. It is a symbol. And in the reverse string, we are making that the first symbol. Whereas in version 2, it is reverse AX is reverse XA. We can also reverse the string by making the first symbol the last symbol. So here in version 2, we are having first symbol and then a string AX. A belongs to sigma, it is a symbol. X belongs to sigma star, it is a string. So we split my input as a symbol string combination and make the first symbol from left is the last symbol. Whereas in version 1, we have a string symbol combination XA. And we make the last symbol the first symbol. So both the things are fine. So both the definitions are correct. In fact, both the definitions are equivalent. We can formally prove that also. Not be doing, but this can be formally proved that both the definitions are equivalent. Formal proof for that is also possible. Fine. So with that note, we move to the next recursive definition. The language of palindrome. Language of palindrome. So palindrome is a subset of sigma star. Assumption: sigma contains two symbols, A comma B. Various combinations of A's and B's possible. Out of that, some of the strings are palindrome. So palindrome is a subset of sigma star. We know the meaning of palindrome. Reading from left to right. It is same as reading from right to left. Many examples are there. Madam, race car. So many such examples are there which are palindrome. A string which is not a palindrome, for example, is students. That is not a palindrome because up to some point it matches, subsequently it does not match. Students, that is not a palindrome. Race car, madam, and other strings are examples of palindromes. In our own language, the Gujarati language, there is a very popular example. Ignoring spaces. If you say, someone knows that Gujarati language example of a palindrome? Very standard example. Involving the village Limdi, I mean town. Yeah, Kaushal, can you just speak out that? Unmute.
Yes, sir. Am I audible?
Yeah.
Yes, sir. The sentence is like that. Limdi game gadi mali. Okay.
Correct. Keval rightly said. Limdi game gadi mali. That is an example of a palindrome. Fine. It's in Gujarati, so that here in English it won't seem to be palindrome. Keval, fine. In Gujarati, we have to write limdi game gadi mali. Ignoring spaces, it becomes a palindrome. Fine. So that is language of palindrome. We are discussing the recursive definition, how to recursively define this language. There are two different ways we can define palindrome. One is the way which we are going to discuss, that is the recursive definition, and the second, that is using some other function. So here's the recursive definition. So here we take the expansion approach wherein we start with the smallest strings that are palindromes, and from existing palindromes, we generate more palindromes. Having said that, what should be my rule number 1? Defining language of palindrome recursively. taking the expansion approach, starting with the strings which are palindrome or basic palindromes, and then defining a way to generate larger palindromes. What should be my rule number 1? For that matter, rule number 2. Assumption sigma is a comma b. Rule number 1, what should be that? Yes, think about that. Smallest palindromes. I suppose you are thinking. Anyone getting idea? Okay, fine. Rule number 1. The null string. Null belongs to PL. The null string is a palindrome. Smallest palindrome, that is the null string. Null belongs to PL. PL is a subset of sigma star. What should be my rule number 2? Again, that is part of the basic strings that are palindromes. Basic strings that are palindromes. What should be that? Keval, any idea? Reverse part we will take up later. Currently is the recursive definition. Keval. Reverse should be same, fine Kaushal, but that is actually our version number 2, which I said involving some function. That is the reverse function actually. Here is the recursive definition. So the smallest string that is palindrome is null, and other strings that are palindromes larger than that, from which we can generate more strings that are palindromes. Rule number 2, after null. Anyone else? So take all input symbols. They are also palindrome. Strings of length 1. Strings of length 1. My sigma contains AB, A comma B. So A is a palindrome, B is a palindrome because the length is 1. So whether you read from left to right or right to left doesn't matter. Null is a palindrome, and the basic palindromes, other basic palindromes are A and B, where A belongs to sigma. So all the symbols are palindromes. That is my rule number 2. All the symbols are palindromes. For any A belonging to sigma, variable A that belongs to sigma, all input alphabets, A belonging to sigma, all input alphabets are palindromes. For any A belonging to sigma, A belongs to palindrome. All elements of sigma are palindromes. These are strings of length 1. Null is a string of length 0. So null belongs to palindrome, that is a string of length 0, and then strings of length 1, all the characters, all the symbols that are there in sigma are palindromes. So for any A belonging to sigma, A belongs to PL. That is my rule number 2. So these are basic palindromes. Null string, then all input alphabets. Now in rule number 3, here the recursive definition will come into the picture. We'll define a mechanism for generating larger palindromes. So how do we write rule number 3? We take the expansion approach. start with the smallest strings that are palindromes and then devise a mechanism to generate more elements, the larger strings. How do we write rule number 3? Say here in rule number 2, suppose I have A, B, these are palindromes. Then my A or BB, that is also palindrome. These strings are also palindromes. So from these basic strings, null, and then A comma B in our example, because sigma equal to A comma B, these are our initial palindromes. And then we can have larger strings that are palindromes. A, BB. Then we can have something like ABA, AAA, BAB, BBB, etc. These are strings of length 3 that are palindromes. So how do we write this formally in rule number 3? Someone should try. Keval or Rikin or Kaushal, someone can try. So in rule number 3, take a string that is already a palindrome and then do something so that the new string becomes a palindrome. So take a string that is already a palindrome, generated using rules 1 and 2, and then do processing so that I can, for example, I can generate palindromes of length 2. So I'll take, say, null string that is also already a palindrome, and then I'll do some processing so that I get strings of length 2 that are palindromes. Exactly, Keval. Add the same character at the beginning and at the last. So take a string that is a palindrome, take X that is element of PL, and then put a symbol A where A belongs to sigma. A means A and B in our example. We are taking A as a variable. Take a symbol, put it at the beginning and at the end to a string already known to be a palindrome. So formally we write that as let X belongs to PL, let X belongs to PL, and A belongs to sigma. A, X, A belongs to PL. X is already a palindrome. For strings of palindrome of length 2, I'll take that X as null. And I'll put A at the front and at the end to generate AA. Or I will put B at the front and at the end to generate the string BB, that is a palindrome. So take an existing palindrome, take a string that is a palindrome, that is let X belongs to PL and A belongs to sigma. So I take any symbol. In our example, we have taken sigma equal to A comma B. That's fine. It could be anything. Sigma could be anything. Our definition is a generic definition. So take an element of sigma, put it at the front and at the end of a string already known to be a palindrome, I generate a new palindrome. And this is true for any length palindrome. Using that definition, I can generate odd length palindromes as well as even length palindrome. So if I, for example, if I start with A, palindrome of length 1, and put B at the front and at the end, I get BAB. So that is odd length palindrome. If I take null and put B at the front and at the end, that is an example of an even length palindrome. Using that, I can generate any length palindrome. And that is my rule number 3. That completes the recursive definition. For any X belonging to PAL and any A belonging to sigma, AXA belongs to PAL. That completes the definition. That is the main part of the definition, rule number 3, the recursive definition. And of course, the rebuttal part, the claim for our claim for completeness. No string is in PAL unless it can be obtained by using rules 1, 2, and 3 above. no string is in PL unless it can be obtained by using rules 1, 2, and 3 above. That is our claim for completeness of the definition. It can generate every palindrome that is existing. The definition generates every palindrome that is existing. And anything that is generated using this definition, of course, is a palindrome. Any string that is generated using our definition is a palindrome, and any palindrome that is existing can be generated using our definition. So that is definition number 2, the recursive definition for the language of palindrome. And it is recursive because in rule number 3, we have taken an existing palindrome and then defined a mechanism for generating new strings that are palindrome. The basic palindromes we started with are null and then input alphabets, that is rule number 2. Null is rule number 1. And using these palindromes, we generated more palindromes. That is my rule number 3. Is it clear? Is the definition clear to all? Okay, Rikin, Keval, Abhi Patel, Jeet, fine. Janil, fine. Next we take, let's see what comes next. Okay, recursive definition for L star will take. Let me see if there is anything else. Okay. Okay, let us follow the same sequence. Recursive definition for, yeah, palindrome. The second definition of palindrome, of course, that is non-recursive definition. It can be using the reverse function, as rightly said, using reverse function. I think Keval had said earlier, the palindrome can also be can be defined in a non-recursive manner, and the definition is this palindrome is equal to, within curly bracket, x belongs to sigma star such that reverse of x is equal to x. This is our non-recursive definition. X belongs to sigma star within curly bracket. X belongs to sigma star, any string in sigma star bar the condition the x is equal to reverse of x. So this is the second definition of language of palindrome using the reverse function. X is equal to reverse of x for x belonging to sigma star. That is version number 2, the definition number 2 involving the reverse function. The definition of reverse could be either version. We have defined 2 versions. You can take any one of these versions for reverse, that is fine. And that is the second definition of language of palindrome, but it is non-recursive. That is not a recursive definition. With that point, now we define recursively L star. In earlier one of the examples, no, we have used this. If L square is a subset of L, then L plus is a subset of L. That was, or a to the power n belongs to L star. A to the power n belongs to L star for n greater than equal to 12. That we had worked out. So that was L star. We have taken L equal to A3 and A7. And then we just listed some of the elements of L star. That is A3, A7, A6, A14, A10, etc., etc. By concatenation of these basic elements, we generate. By concatenation of these basic elements, we generate those elements of L star. Let me see if I can get that. May not be present here. Okay, it's not here, doesn't matter. So let us formally define the language L star. Recursive definition of L star. L is a language over sigma, and I want to generate strings in L star. Sorry. We need to define the set L star. L is a language over some sigma, alphabet sigma. So my rule number 1 is, it is clear, the smallest element that is in L star is the smallest element that is in, let us go to version 1 only. The smallest element in L star is the null string. null belongs to L star. When it is star applied, then automatically it means null belongs to that, because star means 0 or more applications, 0 or more number of times, 0 or more occurrences, or 0 or more applications. So null is the smallest element that is there in L star. L is a language over sigma. When we say L star, it will include null. Null is not part of the input alphabet sigma. But when we say it is star applied, as per the definition of the operation, it will include the string null. Null belongs to L star. In rule number 2, what we do? Take a string that is already in L star and take an element of L, append y to x, that becomes new element in L star. Take an existing element of L star. In our example, for the first time, we'll take that to be null string, and then take y's that belong to L. L is my language. So whatever strings are there in L, we'll append those strings one at a time to the X to generate a new element of L star. In our example, A3 language L was having A3, A7, for example. Then my first element in L star would be null. Then I will take, say, A to the power 3. That is my Y. Y belongs to L. In that example, L is A3, A to the power 3, A to the power 7, A3, A7. So I'll take null, take A to the power 3. To this null, I'll append, I will concatenate, append A3. So null A3, that is A3, will become element of L star. So A3 will become element of L star. Second element, I'll take A7, A to the power 7. To null, I'll append A to the power 7. So A to the power 7 will become element of L star. Similarly, say I take up out of this null A3, A7, for example, I pick up next A to the power 3. That is my X. Currently, elements of L star are null, A3, A7 in our example. So I'll pick up, say, A to the power 3, and I'll pick up A to the power 3 from L. So X is A to the power 3. X is already there in L star. To that, I'll append A to the power 3, Y. Y is there in L. Our L has two elements, A3, A7. So that A3 dot A3, that is A to the power 6. So that will be element of L star. And I can take up all the possible combinations to generate the infinite number of strings which are there in L star. I can generate any string that should be there in L star using this definition. I can generate any string that should be there in L star using this definition, this recursive definition. And no string is in L star unless it can be obtained by using rules 1 and 2. Only 1 and 2 rules are sufficient to generate any string that is there in L star. That completes the recursive definition. Maybe, yeah. Here one more example is taken. Language is A, AB. My language, in our previous discussion, I was talking about A to the power 3 and A to the power 7. Here, example, here L equal to A, AB. Another example, my language contains two strings, A and AB. Two elements are there in L, A and AB. And using rule number 1, null belongs to L star. So one application of, so initial value of L star, initial elements in L star, they are null. And now we look at the recursive portion, the main heart, rule number 2. One application of rule 2, we have null. So taking any element of L star that is null, that's the initial value. To that I append A and then I append AB because L is A, AB. So we have null A, null AB, and due to the property of null, null A is same as A, null AB is same as AB. So these are two new elements in L star, A and AB. So after one application of rule 2, the elements of the set L star are null, A, AB. Null is because of rule number 1, and because of rule number 2, we have appended to null the elements of L. Here are A and AB. Therefore, after one application of rule 2, the elements of L star, they are null, A, AB. For our convenience, we call that L star 1 or L1. let that be L star 1. 1 is for only for our reference, otherwise it is not there, which means one application of rule 2. The recursive definition is rule 2, and elements of L star after one application, they are null AAB. Similarly, we go with the second application of rule 2. Once more we apply, so null AAB are already there, and then we concatenate this, all the possible combinations that we take, null AAB. To that we concatenate A, comma AB. A and AB are elements of L, and if we do the concatenation null AAB within curly bracket, concatenation with A, comma AB, we get all these combinations. Null AAB already there, and then we have AAB, ABA, AA, AB, AB. So that is the second application of rule number 2. Our rule number 2. Existing elements are null AAB, and we take the concatenation AAB. So we are not taking all the, I'm not discussing all the things, but see, take AB from the first set. We are concatenating to that another AB to generate AB, AB. Or we may take A from the first set, that is the existing elements of L star, and the elements of L which are AAB. From both I pick up A, I get double A. Similarly, you can get the remaining strings generated due to the second application of rule number 2. These are the elements in L star. In the same way, a string in general, just our observation is only the observation. In the same way, a string obtained by concatenating k elements of L can be obtained by k applications of rule 2. This is an observation. Otherwise, I mean, even if you don't get it out, get that doesn't matter. Concatenating in the same way, a string obtained by concatenating k elements of L can be obtained by k applications of rule 2. For example, I take L to the power 2 contains AB, AB. In the set L square, one of the string is AB, AB, and that is AB, AB is obtained by k elements of L. It is obtained by 2 elements of L. AB, that's the first element, and again repetition of AB. So that is AB, AB, a string that is obtained by concatenating k elements of L. So it is AB, AB. By concatenating 2 elements of L can be obtained by k applications of rule 2. So this AB, AB, it is obtained by 2 applications of rule 2, just for our observation. Just for our observation. You take, similarly, we can take A and AB. So there are 2 elements present, A and AB. So by concatenating 2 elements of L, we get AAB. So that is there in L square. It is there, it is obtained by 2 applications of rule 2. So that will be element of L square or L star square. This is just for our understanding. As far as the recursive definition is concerned, this is the only definition. What is the meaning of this definition? Particularly rule number 2, just we have explained, taking this example. Otherwise, we should not worry whether how many applications of rule 2 are there. Using this recursive definition, step number 1, 2, 3, we can generate any element of L star. We can generate all the strings that are in L star, and whatever is generated using this definition is definitely there in L star. So that is my rule number 3, my claim for completeness. No string is in L star unless it can be obtained by using rules 1 and 2. Just to understand the second application, rule number 2 particularly, we have taken this example, and what we get initially, that is null belongs to L star. Applying rule number 2 once, for our understanding we have said L to the power 1, and applying rule number 2 second time, we get these strings. So these are all actually elements of L star. How many times we apply the rule 2 actually does not matter. We should be able to generate a string that is there in L star, applying some applications of rule number 2. Fine. Maybe very quickly, second way. This is one definition of L star, version 1. We could have defined this alternatively also, and this is the alternative definition of L star. Minor changes would be there. not much. Version number 2. So what we do? Null belongs to L star, no change. Rule number 1, null belongs to L star in both the versions are same. So that is null belongs to L star. Second, what we do? We copy the strings that are there in L into L star. That we didn't do in the previous version. Here we explicitly copy elements of L into L star. So for any x belonging to L, x belongs to L star. We copy all the elements of L into L star. That is rule number 2. So separately we are copying and then we concatenate. For any two elements x and y of L star, x, y belongs to L star. Same way we do the concatenation. Like rule number 2, similar to rule number 2. Here we start with null belonging to L star. Then whatever elements are there in L, for example, L contains a comma ab. So we copy this a and ab into L star. So we have null a ab after applying rules 1 and 2, version 2. For any x that is there in L, we copy into L star. And then now we have L star containing null in the elements, basic elements of L. And then we concatenate two elements of L star itself. So for any two elements of x and y of L star, x, y belongs to L star. So that is the second version. Whereas here what we did, we didn't explicitly copy elements of L into L star. Rather, we have concatenated. In rule number 2 itself, we have included. So we take an element of L star to begin with, null, and then we take any element of L, and then we concatenate, get x, y belonging to L star. So that is how actually the steps 2 and 3 of this version number 2 and 3 is clubbed and taken care in a single rule. That is taken care in a single rule. Here we are concatenating element of L star and element of L, whereas we explicitly copy elements of L into L star. And once that is done, we concatenate two elements of L star to generate all the strings that are in L star. That is using rule number 3. That is step number 3 or rule number 3 in the definition. Now once again, both the definitions are equal and defines L star precisely. Again, formally this can be proved. Both the definitions are equal and defines L star. So that was another example, recursive definition of L star. Any doubt? Is that clear, students? Is that clear? Recursive definition of L star, is that clear? Yes, Keval, Rikin, fine, Janil, Abhi, Harsh Tumar. Any doubt to anyone? Okay. So next we recursively define, let's see, I think language of fully parenthesized algebraic expression. Let us define this recursively. So currently we are discussing the recursive definitions topic. That is part of chapter number 2. The earlier was principle of mathematical induction and other proof techniques. Currently we are in the second half of chapter number 2. Recursive definition, principle of mathematical induction and other proof techniques, and recursive definitions. So we have seen some of the recursive definitions. For example, L star, the language of Palindrome that we saw, and then the reverse function, recursive definition for the reverse function. These things, and of course factorial is the standard recursive definition. And then we have seen recursive definitions dealing with the strings like reverse, recursive definition for palindrome, and L star dealing with handling strings. Fine. Next recursive definition, next example of a recursive definition is that of a fully parenthesized algebraic expressions, and here are the assumptions. Recursive definition for the language of fully parenthesized algebraic expressions. Assumption is sigma contains alphabet. Elements of sigma, there are 5 elements. there are 5 elements: identifier I, opening parenthesis, closing parenthesis, plus and minus. There are 2 binary operators, plus and minus. 2 parentheses we are using, the opening parenthesis and the closing parenthesis, and identifier I. So sigma contains only 5 elements. The definition remains the same. Even whatever the approach that we have taken remains the same, even if there are different number of elements in sigma. Just for simplification, the assumption is sigma, which is our input alphabet set, contains 5 elements: identifier I, the opening parenthesis, the closing parenthesis, and the operators plus and minus. And these are plus and minus are binary operators. Identifier is I, and meaning of the fully parenthesized algebraic expression is exactly 1 pair of parentheses for every operator. The meaning of fully parenthesized algebraic expression is that exactly 1 pair of parentheses for every operator. For every operator. So if I say I plus I in parenthesis, within parenthesis, bracket, and within bracket what I write, I plus I, then it is an example of a fully parenthesized algebraic expression. But if I say double bracket, double opening bracket, I plus I, double closing bracket, so within 2 brackets, I plus I, that is not a fully parenthesized algebraic expression, because there is 1 operator plus and I have 2 pairs of parentheses. The definition is exactly 1 pair of parentheses for every operator. Now we define recursively fully parenthesized algebraic expression. No. The examples of strings in AE. AE is our language, fully parenthesized algebraic expression. That is our language AE. So I, identifier I, there is no operator, no parenthesis. 0 operator, 0 parenthesis. Bracket I plus I, bracket I minus, maybe I plus I, minus I, one more parenthesis. There are 2 operators, 2 parentheses, that is fine. So these are all examples. Double opening bracket, or just bracket I, that is also not fully parenthesized algebraic expression. Bracket, then I, bracket over, bracket starts, I, bracket over, that is also not fully parenthesized algebraic expression. Fine, let us define that. I have already shown the first rule. Let us recursively define fully parenthesized algebraic expression. To that we call AE. Our language is AE. So let us define the language AE. And my rule number 1 is identifier I belongs to AE. The smallest fully parenthesized algebraic expression is the identifier I. So I belongs to AE. I belongs to AE. I belongs to AE. Okay, fine. So what should be my other rules? Let me stop presenting. I think I was not getting that chat window. Fine. Try to define that by the time I reload my presentation. Try to define this fully parenthesized algebraic expression. I don't know. Without stopping. Define that by the time I reload this presentation. Define this, write down the definition, assumptions we have seen. Meanwhile, I'll reload this presentation. Am I audible? Hello? Okay, fine. So let us continue this definition, what you have written. Let's see. Anyone wants to speak out the definition? One is I belongs to AE. The smallest string that is in AE is identifier I. Which are other strings? What should be rule number 2? The recursive way for generating more elements in AE. How do we do that? Anyone? How do we write rule number 2? Keval, you want to try out? Okay. So maybe let me write. Take two elements that are already there in AE for any x and y in AE. Both bracket x plus y and bracket x minus y are elements of AE. So take two elements that are fully parenthesized and apply operator plus, and at the same time apply this parenthesis. For one operator there has to be one pair of parentheses. So with plus I am applying this bracket, opening bracket, closing bracket. Similarly with minus also I am applying the opening and the closing bracket. So when I apply an operator, I also apply the plus, the parenthesis. So for every operator, there has to be one pair of parentheses, exactly one pair of parentheses. So with plus, with the operator, I am putting that pair also. So there cannot be mismatching of that. And in our example, this x plus y means that is I repeating itself. That becomes I plus I. We are taking only identifier I. So x and y have same value, that is I. So that becomes bracket I plus I and bracket I minus I. These were new algebraic expressions. My first answer is I, and then I repeat x and y. X and y I take same, that is I. So bracket I plus I and bracket I minus I. These are new elements of A, and then I can take further combination. Maybe bracket I plus I minus I, again within bracket, that becomes new fully parenthesized algebraic expression, and so on. Main idea in rule number 2 is I require exactly one pair of parentheses for every operator. That is the requirement. So what I do with the operator, I also write the parenthesis in the correct expression. So as soon as I apply an operator, I also have one pair of parentheses. So it is ensured that for every operator, there is exactly one pair of parentheses. And of course, rule number 3 is my rebuttal part. No string is in AE unless it can be obtained by using rules 1 and 2. So that is the fully parenthesized algebraic expressions. And here you can generate, say, I because of rule number 1. Then take x equal to I and y equal to I. So bracket I plus I and bracket I minus I. These are my next expressions. And then take x equal to I plus I in bracket, y equal to I. So this is in bracket I plus I minus I and in bracket. So that is bracket x minus y, where x I have taken as within parenthesis I plus I and y I have taken as I. So I get within bracket I plus I, again in bracket minus I, and I can generate any string that is a fully parenthesized algebraic expression using rules 1 and 2 above. That is my rule number 3 in the definition. Is that fine? Is that fine? Kaushal, okay. Abhi, fine. Keval, Rikin, Janil, good. Harsh is there. Harsh Tumar, still connected. Okay, fine. Fine. This we have already defined, palindrome. Let us define, next let us define finite subset of the natural numbers. Finite subset of the set of natural numbers. We recursively define the finite subsets of the set of natural numbers. We define a set F of all the subset of the natural numbers. We define set F of all the subset of the natural numbers. Think about this definition. In fact, the rule number 1 is visible. Phi belongs to F, the empty set. Empty set, that is a subset of every set. So it has to be there in F. F is a set of subsets of natural numbers. All the possible subsets should be there in F. Finite subsets of the natural numbers. Any finite subset of natural numbers should be there in F. We define a set F of subset of finite subsets of natural numbers. And the first subset of natural number, that is phi. Phi is a subset of every set. So phi belongs to F is my rule number 1. Phi belongs to F is my rule number 1. How do we define? How do we add elements to F? F contains all the subsets, all the finite subset of natural numbers. So F is a set of subsets of natural numbers. So you take any subset of natural number, for example 159, that has to be there in F, or maybe 1,2, that subset has to be there in F. So how do we define F, the set of subsets of natural numbers? How do we define that? So smallest element that we put in F is the empty set. Phi is a subset of every set, so phi belongs to F. And I must be able to add all the subset of natural numbers to F. It is a requirement. How do we do that? How do we expand F? How do we expand F? We have started by putting phi in F. First element that we have put in F is phi. Think about that. How do we expand F? How do we expand F? Anyone would want to speak out? How do we expand F? Phi is empty set. Next, we may take subset of, we may consider subset of cardinality 1. We may, phi is empty set, so cardinality is 0. Then we can take subsets of cardinality 1. It means all the subsets having single element. All the subsets having single element. F should contain all the subsets. So it should contain all the single element subset of N. All of them has to be there in F. Single element subsets of natural number has to be there in F, as F is a set of subset of N. So we go step by step. We started with phi, no element, the empty set. Then we are taking single element subset. How do we write this? How do we formally write this? Single element subset has to be there in F. How do we formally write that? Anyone? Rikin, maybe you want to try it out? Rikin, you are there? Are you there? Janil, are you there? I hope someone is there. At least someone is there. So single element subset, it's not difficult to write. You take a natural number and then apply the set bracket. So you take any small n belonging to capital N, the set of natural numbers. Then within bracket N would be there in F. See, single element subset. So take a natural number. take a natural number. Let small n belongs to this capital N. N is a set of capital N is a set of natural numbers. Then within curly bracket n, within curly bracket small n belongs to f. That is my rule number 2. That is the second rule. Let me see. Yeah. For any n belongs to n, where n is a set of natural numbers, bracket n, curly bracket n belongs to f. So you take a natural number, say 1. So that will be bracket 1, bracket 2, bracket 3, bracket 4, so on, so forth. All of them are there in f. Has to be there. F contains all the subsets. So subset having cardinality 1 has to be there in f. So we have taken 5. Then we have taken something like bracket 1, bracket 2, bracket 3, bracket 4, bracket 5, bracket 6. Any natural number you think, it is included in f. For any n belonging to n, the set of natural numbers, capital N is the set of natural numbers. Curly bracket n, within curly bracket n belongs to f is my rule number 2. In rule number 3, I must define a mechanism for including larger subsets in f. For example, 1, 2, 1, 3, 1, 4, 2, 3, 2, 5. Any possible combination has to be there in f. Not only that, I mean these not only length 2, cardinality 2, but something like 1, 2, 3, 1, 9, 12. All the combinations I should be able to include in f, and that will be my rule number 3. How should I write rule number 3? How should I write rule number 3? Using some set operator, we can define that. That is a clue. Am I audible? Am I audible? Okay. Keval, you want to try out this? Keval, you want to speak out without thinking? Fine, doesn't matter. See, take a very popular set operation. Take union and apply. Take any two set of f and apply this. You get the answer. Take any two elements in f and apply the set union. You can generate all the subsets. So that is rule number 3. That is rule number 3. For any a and b in f, for example, we have something like bracket 1, bracket 2. Already all single element subsets are included in f using rule 1 and 2. 5, then bracket 1, bracket 2, bracket 3, etc., etc. So I pick up any two elements in f and apply set operation. So using that, I can generate all the 2 cardinality subsets to begin with. Then I can take a 2 cardinality set and a 1 cardinality set, for example, bracket 1, 2 and bracket 3, and apply union. I get 1, 2, 3. In that way, any cardinality set I can generate using rule number 3, and that completes my definition. The most important part is rule number 3. Take any two existing element in f. At the moment, I have the 5 as well as single element subset in f. Pick up any two existing element in f, apply the set operator union. You can generate any finite subset of n, include that in f. So take any two elements in f. Already we have 5 and single cardinality subset, apply union, get the new element in f. In that way, I can get all the elements of f. That completes the definition. Nothing is in f unless it can be obtained using rules 1, 2, 3 above. So with that, we complete this recursive definition in today's class. We'll continue in the next lecture, maybe in the next week. Thank you.